If you were here at ODSC West last time, you might remember that GIF. But I just really like the GIF. This was around work that we were doing at the New York Times to model the emotions that were present in certain articles. And that's not exactly what this presentation is about. But hopefully this presentation gives you some news, and it will make you either happy or sad. So the GIF is broadly relevant. But let's start with the basic premise of this presentation, something that should be very familiar to all you guys, and which ODSC is largely about, is that as data becomes more available and modeling techniques become more complex and accurate, machine learning models are being deployed in different aspects of society that are affecting real people. Now, what does this mean? Well, to give you an example, for credit scoring applications, when you're applying for a loan, there might be a lot of features that are impacting you in ways that you don't know. So Bloomberg reported that whether or not you own an Android phone could have an impact on if you get a loan or not. Forbes recently reported about research going on into personality types. So depending on your personality type, you might have a better shot or a worse shot of getting a loan. Meanwhile, at the same time, there's a growing appetite to understand machine learning models. Journalists are doing more to probe the machine learning models in our society. So Wired recently ran a bunch of tests on Google's photo algorithm. This was recently, a software engineer at Google had discovered that their photo tagging algorithm was labeling some people as gorillas. And so Wired decided to dig into this a little bit. The New York Times just this month tried to dig into targeted advertising and see why people were being served certain ads, what sort of decisions that ad providers could make to target people. And so this one was saying, target everyone that's trying to lose weight but still loves bakeries. So that's me, basically. Spiegel, actually, this was a couple of years ago, they ran this really cool controlled experiment in the housing market. So in Germany, at least over the last couple of years, Germany has been struggling to absorb millions of migrants. And that has played out in a lot of different ways in society. And so what Spiegel was testing was, if there's two people that have identical applications, one of them has a Syrian-sounding name and one of them has a Germanic-sounding name, will that Germanic-sounding name get more callbacks than the Syrian-sounding name? So there's a lot of different techniques out there for probing the algorithms in our society. And what we're trying to say here is that we need more techniques. The more techniques we have out there, the better we can understand the impact that machine learning models are having in our lives. So this work is called actionable recourse and linear classification. I'll define what actionable recourse means. We are focused on linear classifiers at this stage, which I know is not that exciting for you guys. You guys want a lot of deep learning and stuff. We're moving in that direction. But this work came when I was still at the New York Times, and we were looking at subscriber models. And so we were trying to understand why certain subscribers got certain discounts, whether we can introduce more transparency into that, and maybe at some point make it more fair. But in doing so, we connected with Burke and Yang at Harvard, and they're doing a lot of work in this space. And so this work came out of that. But first, a little bit about me. I was at the New York Times for 4 years as a data scientist. I was working with a lot of journalists and business side stakeholders. From there, I went to Microsoft Research. We were looking at fake news and misinformation and Russian propaganda spearheaded by the Internet Research Agency in the US elections. I'm currently a PhD student at Carnegie Mellon, where we're working with NASA stakeholders to help them organize their scientific articles, to make it easier for scientists to find collaborators and data sets of interest, et cetera. Hopefully at an upcoming ODSC, I can talk about that a little bit more. Yeah, I'm broadly interested in applications of machine learning to journalism and helping journalists find information more easily. But thank you for your time. I hope this presentation is interesting to you guys. I will first go through a bit more introduction and motivation. Then I'll go to the methodology, We have some experiments that we use these tools to show, some broad demonstrations. We'll end with a short discussion, hopefully a demo if there's time. But stop me at any point if you have any questions. I love answering questions, even if it's mid-sentence, just raise your hand. OK, so let's put ourselves in the shoes of a practitioner, of a data scientist, as I'm sure we've all been there. You have a data set. In this data set, each point represents an individual. And the points are blue if that individual is labeled a good customer, or they're likely to pay back their loan. It's labeled a red if that person has failed to pay back their loan in the past, or they're labeled a bad customer. And what you're trying to do is model, can I predict in the future, can I predict whether a customer is going to be good or bad? So you fit your line. You have pretty good accuracy. And you say, great, OK, I'm ready to deploy. Now, let's look at what happens to these individuals that are being scored. So under this model, under this static model, assuming the model doesn't get retrained or anything changes, what if you are that person? So that person doesn't have good credit. They don't have a lot of savings. They apply for a loan. They're probably going to get rejected. Now, if you are that person, what can you do? Well, you can increase your credit a bunch, or you can increase your savings, some combination of the two. And maybe you can get to that decision boundary. Maybe you can get approved for that loan. And that's great. That's a good outcome. But let's say that one of those axes is not credit, but it's something like age. So you don't have many choices in this case. If that's the decision boundary and age is one of the main factors, I mean, what are you going to do? Wait 10 years to get that loan? What if that access was something else, like gender or race? You wouldn't be able to get access to that loan. I mean, there's another example. Maybe you can change that access, but you can't change it in the right direction. So there's a lot of research that shows that as you go from your bachelor's to your master's degree, you become more creditworthy, and that's great. But as you go from your master's to your PhD, you actually become less creditworthy, which is unfortunate. But once you get your PhD, it's not like you can just say, oh, just kidding, I'm just a master's. Not just a master's. Master's is a very respectable degree. But there's a sort of directionality implied here. So once you move in one direction, you can't go back. So clearly, there's many reasons why an individual under a machine learning model might not have access to a prediction that benefits them. Right now, I mean, there's a lot of fair and just reasons why that is the case in society. But there's just no way to systematically evaluate this. And decision-making practices have been happening way before machine learning. The exciting thing about machine learning making these practices is that we can start to interrogate these models. And we can start to say, well, OK, can we systematically understand who is being denied access to this recourse, to this resource? Can we systematically understand what it costs to get access to this resource? And that's what we're talking about here. So we've formalized this concept called recourse, where recourse we're defining as an individual's ability to gain access to some resource. So an individual's ability to flip their prediction in a machine learning model. So a person has recourse if there's some realistic set of changes they can make that will get them to the +1 in the machine learning model. And they don't have recourse if their prediction depends on immutable variables like age or race, or the set of changes imposes some sort of excessive cost on that person. Now, there's a lot of terms that I've thrown up here, and I'll go and define them later in this presentation. But first, just to solidify, what do we mean by actionable input variables? Well, we talked about in the beginning personality types. Unless you're literally crazy, you probably can't change your personality type. There are other variables that might be conditionally immutable. So the direction matters. Once you move in some direction, you can't move back. And then there's other variables that are mutable, but it's probably not realistic to expect people to change them for access to some resource. So a really bad pickup line if you're trying to propose to your significant other is, hey, will you marry me so that we can get this loan? So clearly, there's a lot of reasons why an individual might not have recourse under a machine learning model. And in this work, well, first let's ask, why does that matter? I mean, maybe this is OK. Well, for over 40 years, a right to an explanation has existed in society. So starting in 1974, the Equal Opportunity Credit Act required people that were denied access to something, whether that's hiring or housing or something else, required them to have the right to an explanation. So why were you denied? Right now, those explanations take the form of an adverse action notice. So this is one I just pulled off of online. And this is an actual adverse action notice. It can be very simple. So this person was denied a loan. And then the bank said, well, you were denied because you had insufficient bank references. Maybe you were working on the wrong job. You had insufficient credit experience. I hope none of you have been denied loans, but I'm sure that in some sense, we're all familiar with this if we've ever checked our credit reports or something. Now, this is great. This definitely helps us understand a little bit about ourselves and why we were denied. But it doesn't really tell us how we can be approved. We have no guarantees here. So we know that maybe we're working in the wrong job or we have insufficient bank references. But how many more bank references should I get? Should I get 3 references or 5 references? If I get these references, do I know that for sure I will get that loan? No, this explanation doesn't really tell us that much about what we need to do. What if we had something that was very concrete? So here, what we're calling a flip set, it's a set of different actions that you can take. Each one of those sets is guaranteed to flip your prediction. So for example, if you wanted to flip your prediction, you might increase the most recent payment amount from $0 to $800. And that's great. That will flip your prediction. And maybe that's outside of your reach. So if you can't do that, then maybe you can increase your most recent payment by $500 and then go 2 months with 0 balance instead of a negative balance instead of 1 month. So instead of providing individuals with just a set of explanations, maybe we can provide them with concrete actions to take.
Can I ask a question? Maybe you'll get to this, but I know in my work, some of the fear of too much transparency is enabling people to game the system. And so what are your thoughts on that, or are you going to touch on that at all?
Yeah, I mean, reverse engineering algorithms would totally be a reason why people wouldn't want to do this. But explanations are part of US law. And as more models are deployed in society, I mean, maybe regulations will increase to the point at which this becomes required. Also, as ethical data scientists, maybe we might not be providing people with explanations, but we might want to audit our models before we deploy them to make sure that we're not being biased on a certain variable, or we're not limiting people for recourse in society. I mean, maybe we don't show that to people, but we still sort of check before we deploy. And yeah, I mean, this presentation is focused around loans, just as an example, but this is broadly relevant to any sort of resource that we might be providing people. So food stamps, benefits, subscription discounts, which is where this actually started in. So explanations aren't actionable, as we talked about. They're also not contestable. There's many reasons to explain a prediction, and we could be explaining a prediction with a totally valid set of things like, your credit wasn't good enough, when really there could be a factor like race or gender that is the true driver of that decision. So there's many ways to explain a prediction. And this actually, this is actually a very common tactic to sort of hide other variables like whether or not you're using the Android phone as a signal. You might not want to show that to people, so you might explain it using a different set of correlative variables. sort of hide what's actually going on. But then most importantly, as data scientists, we all love quantification. Explanations aren't quantifiable in the same way that a flip set or an action set would be. So we can't say things like, 20% of our population has no recourse under this model. Or, of those who do have recourse, it costs X. We can't really say that with just a set of explanations. So in this work, I'll talk a little bit more about the problem, and then I'll present some software, hopefully a demo at the end if we have time. And this routine, this optimization routine, is completely independent from your model development. So you can do what you've been doing, and maybe this is just a way to check at the end. So the kinds of things that we can answer are, for each individual, what can they do to flip their prediction? And then over an entire population, how many people are denied recourse, and what's the cost of recourse? We hope that such tools can help practitioners, such as yourselves, machine learning experts and engineers, journalists who want to investigate algorithms, government agencies who are thinking about how to regulate algorithms, and consumer advocates. And I'll pause there for any other questions. OK. So when we started off looking at this problem, we tried the naive brute force approach, which was just a big search over the space. So what kind of actions are possible to change, and what are all possible combinations? How many of them flip the prediction, and what's the lowest cost one? And this is a great place. We always start with the most naive approach, but of course that's memory inefficient. So the one that we went to eventually was an optimization approach. And I'll pause here to talk a little bit about optimization. If you haven't used optimization yet as a practitioner, optimization tools are a really amazing way to solve problems. Because if you can specify your problem in an optimization formulation, there's a lot of black box tools out there that will quickly and easily solve your problem. Furthermore, expressing your problem as an optimization problem allows you to get right at what you actually want to solve. So what do I mean by that? Well, there's a lot of machine learning models that will solve some related optimization, like, for example, SVM tries to maximize the margin between two disjoint sets. And that's great, but what you're really trying to do is to maximize your accuracy. So SVM sort of assumes that maximizing that margin will get you there, but that's not necessarily what's going to actually maximize your accuracy. So if you can formulate your problem as an optimization problem, you can get very close to what you actually want to solve. And they're also very simple. I mean, this is just a couple lines. Obviously, I'll walk through the full specification in just a slide. But what this says, what all optimization problems are formulated around, so there's an optimization objective. So in this case, we want to minimize the cost of X and A, where A is the actions that we're asking the user to take, and X is their input variables. We want to minimize the cost subject to constraints. So here our constraint is that the actions need to flip the prediction. So F is our decision-making function. So F of the input variables plus whatever actions we're asking the user to take must result in a positive 1. And that's it. So it's very simple. And I'll go through the full specification now. But again, we want to minimize the cost. And cost is a black box function. I'll get to that in a couple slides. This is the equation that we had above as F. Since we're dealing with linear classifiers, we can formulate this as just a convex sum of the weights, W, the coefficients, of the input variable plus whatever action we're asking the user to take. And we're saying that that must be greater or equal to 0, because that must flip the prediction. What is A? Well, what this step is saying is that we're discretizing the actions. So each dimension, the possible actions, we're chunking them up. So we're saying, so if we're asking you to increase your savings, let's ask in increments of $50. So increase your savings by $50 or $100 or $200. we've shown in our paper that this discretization doesn't affect the availability of recourse. So if we're discretizing in fine-grained steps, that's the same thing as a continuous formulation. And here, VJK represents a dummy variable. So VJK is 0 if that step is not being taken, and it's a 1 if it is being taken. So if we're asking you to save $100 more, that VJK would be 1. If we're not, then that VJK would be 0. And we want to add one additional constraint to make sure that there's only one step being asked in each dimension. So what this step says is that out of all the different chunks that we're asking people to do, there can only be either one being taken. So either one of the VJKs can be 1, or none of them can be, in which case a dummy variable u represents the fact that we're not asking someone to take an action in that dimension. And that's it. These are just definitions of variables. So that sort of highlights the expressive power of optimization equations in that we only have to specify 4 different lines, and then we have black box solvers, so like Cplex that IBM produced, or CBC, which is an open source optimization solver. Python actually wraps a lot of different solvers into some very generic interfaces like Pyomo, which is very, very convenient as a practitioner. But let me get to the cost. So we've called this a black box function. Cost is a very tricky thing to assess. Hopefully, as a domain expert, you might have a more nuanced view of what cost means for your problem. So what does it mean to ask someone to move to a different state or to increase their credit? What sort of cost does that impose? What we did in our work was we took a sort of more naive approach just based on percentile shifts. So a percentile shift just says, this is your dimension, savings. We're asking you to move to the 60th percentile of savings to the 80th percentile of savings. That's a 0.2 percentile shift. And that would be the same as moving from maybe the 40th percentile to the 60th percentile, even though the amount itself is not different. Sorry, even though the amount itself is a different range, the percentile matters. Now, we chose this just because it was easy. It was sort of domain agnostic, and we could learn it from our training data by looking at these distributions. But it's by no means the best cost. I mean, we're definitely looking in future work to sort of expand what we mean by costs. But using this concept of percentile shifts, there's a couple different costs that we can formulate. One of them, which is the most simple, is just out of all the dimensions that we're asking you to change, which one has the maximum shift? So if we're asking you to shift your savings by 0.5, that would be your cost, regardless of whether if you have to change a lot of other things. So you can see the shortcomings here. We can ask you to increase your savings by 0.5 and do a lot of other things, but those other things aren't reflected in the cost. However, it's very interpretable. If I say that this user has a cost of 0.5, that means that one of their features they need to shift by 0.5. So we can look at that and easily understand what's going on. An additional formulation might be involving the sum. And now this would capture, so the sum operation sums over all the different dimensions. And this captures the idea that maybe we're asking you to do a lot of different shifts in a lot of different dimensions, and we want to add that to the cost. This log over here is just capturing the observation that maybe it's harder to shift on the upper scales of the distribution. So most, as we all know, most real-world data is very heavily tailed. So moving from the 95th percentile of income, say, to the 98th percentile of income might involve making millions and millions of more dollars, especially here in Boston where the cost of living is high. But moving from the 50th to the 52nd might be a little bit less. So these are just 2 different ways of formulating the cost. Obviously, we can think of more different ways. But once we have all these pieces, the routine becomes very simple. So the practitioner, all they have to specify is some sort of input model, And then for each user, they have to give input data and maybe a set of actions. They have to specify what is immutable and what is not. But given these things, they all go into the optimization problem, and we can say either a flip set exists for this person at this cost, or if we can't find a flip set, that's proof that this person doesn't have recourse, given their input variables to this model. It's very fast, so it runs under 1/100th of a second for most problems that we looked at. It works for all data types. You can specify your cost functions, and it works for any linear classification model right now. So logistic regression, SVMs, rule sets. The speed is what is really great because it allows you to scale this across data sets of hundreds of thousands of users to check a broad population of users. OK, so now that we've developed these tools, we started to look at a lot of different problems that might arise in machine learning. And we have 3 examples here, but I'd be really curious if you guys have other examples or thoughts in this domain. But the first thing we looked at is something that should be very familiar to all of us as practitioners. What are the small changes that we make when we're doing modeling exercises? So even in logistic regression, simple as it is, there's a lot of different parameters that you can tune. So you can tune like the L1 loss, or you can tune the L2 loss. L2 will constrain the size of your coefficients. L1 will encourage more sparsity in your coefficients. And this is great. I mean, as the practitioner, you can look at the error that your model is producing, and you can say, OK, well, I see a lot of different models here that are pretty much performing the same. So this broad class of models from 10 to the 0 to 10 to the 2, they all pretty much do the same. And we've all faced this as practitioners, where we're trying to do our best to quantitatively check all different kinds of tweaks that we can make. But at the end of the day, there's a couple that do the same. And how do we choose? Well, I don't know. We could choose that one, or we can choose this one. If you're thinking about recourse, if you're thinking about what are the effects of my model on my population, I mean, there's some things that you can do even out of the gate, especially with sparse models. You can look at how many coefficients are not 0. So in this problem domain, we had 16 dimensions. We said 8 of them were actionable by looking at them. And you can see that as we increase the sparsity in our model up to 10 to the negative 2, we have more of these actionable variables that have 0 coefficients. And so the more coefficients are 0, the more input variables the user has, the less input variables the user has to change. So if the coefficient is 0 and they change that feature, there's no movement that happens in the space. Now, what effect does this have when we can start to look at recourse? We can see that even within the scope of broadly equivalent models, the recourse for our population starts to decline. Even at maybe 10 to the 2.5, we're still within a very similar predictive error. But suddenly, the recourse for our population has dropped by more than 50%. Obviously, the cost has also started to rise. And so this is important for a practitioner, because out of the gate, when you're looking at different models to choose, you might not even realize, you might be trying to do your best, but some of the choices you might make could have adverse effects on the people that you're affecting. And what we're trying to do here is just give another tool to quantify. This is I showed this a couple of slides before. I mean, this was generated directly from this experiment. So this is, for one individual, these are the kinds of changes that they can make to get to that decision boundary. Now, the second experiment we looked at was dealing with training samples, or the sampled population. This has long been studied in the context of statistics and sociology. I mean, when you're taking a sample of a population, you want to make sure that that sample accurately reflects the distribution of dimensions in your population. But what does that mean in terms of recourse? Well, this is just one thing we looked at in terms of credit and loans. So for young people often are rated as worse customers for loans, and this becomes a vicious cycle. If you're a young person and you don't have a history of loans before, then you're more likely to be excluded from a machine learning model because you're less likely to get a loan in the first place. And the dimensions that have signal for you are less likely to be represented in that model. So when we take our training sample, this first graph shows just our entire training sample, which includes a bunch of young people in it. But then when we artificially exclude those people from that sample, we create a model that the weights are slightly different. And this starts to impose a lot more cost on the young people in this model. What does this mean specifically? Well, if we look at a specific action set for a young person, underneath the bias classifier, we might be asking them to change their monthly income from $3,000 to $23,000, which is a huge shift. Whereas in the baseline classifier, we might be asking them to make a much smaller shift. What this is capturing is that the coefficient for monthly income is a lot smaller in the bias classifier. And that's because this variable might have a lot of signal for different parts of the population. Like maybe for young people, there's a lot of signal in how much income you have. But for older people, maybe there's other variables that carry more signal. And so those are greater coefficients in the model. So your ability to pay back loans in the past because you've gotten a lot of loans because you're older, that has a lot more signal. Whereas for a younger person, they don't have a long history of loans. So there's other features that might carry signal. This is why we might see some subtle differences in these models. Yeah, I would not want to be asked to go from making $36,000 a year to like over $250,000 a year. It's a huge jump. The third thing we looked at was demographic differences. Now, this is something that's broadly interesting to me, and I think a lot of people that look at transparency in machine learning, they ask, how does this model adversely impact different subpopulations? So males versus females, different races. And here, we looked at a lot of things, but broadly across the spectrum, we found that in the sample populations that we looked at, females had a lot higher costs of recourse than males did. So this gives you sort of a sense of sort of the things that you can do, the ways that you can look at different subpopulations in your model. And any questions at this point?
How do you control for various proxies between those demographic things? Like, generally use zip codes to figure out some of the races based on like history of redlining in certain areas. So how is there a way you can control that, or is this that a little bit beyond scope?
In our data sets that we looked at, gender was considered. Gender was explicitly observed. But you're right in that, obviously, confounding situations exist with, geographic area might capture confounders for race or gender. And again, linear models sort of make a very strict assumption that there's no confounding that exists, which is one of their great shortcomings. But, I mean, this is why when adverse action notices say that, like, you were denied because of X, Y, Z, that might not be the whole reason. And a flip set, might suffer from the same things. But if you have a linear model in production that's being deployed and that's scoring people, regardless of what confounders exist in your training data, you will still be able to flip your prediction by moving in one direction. Even if it's confounded by other things, I mean, that machine learning model will still allow you to move along the hyperplane. So, I mean, obviously that's not true for more complicated models, but there's ways that we can look at complicated models and then formulate them as linear models. Like you might be familiar with LIME, which is LIME is a method for taking a complicated nonlinear model and then making local linear approximations to that. And that's some of the things that we're starting to look at in the future. Yeah.
Try to apply any sort of recourse model. You need to understand, there has to be some transparency in the original prediction, and that can't be easy, right? I mean, we had the example of, here's an explanation of why you didn't get that loan, but it gave, it gave partial answers. In, the case of, say, Facebook's recent stupid housing and mortgage recommendation thing, where they basically did what they always do, which is reinforce biases.
Yeah.
It was pretty plain to people saying, hey, wait a minute, you didn't even really need to see the details of the model, but others are, are more subtle. So the question is, what can we do to get more transparency in various models across various industries?
For sure. So all of these demos and sort of the way I've framed the problem so far assumes that you have complete access to both the training data and the specific model that is being used, which is an extreme assumption. But there's still ways that you can, even if it's a black box model, there's still ways that you can get close to what's happening. So like a journalist, like at Wired, they're submitting a lot of photos to Google's algorithm. And they can take the results of those photos and they can construct their own models around that can approach the accuracies of those models. And so there are ways to reverse engineer sort of the models that exist in society in ways that can give insight into those models. But of course, it doesn't approach the benefits of having complete access. But for the context of this audience and sort of the discussion, I mean, maybe, well, we, as machine learning practitioners, we're not necessarily unethical people. We want to make sure that we're doing the best that we can before we deploy our own models in society. So there's a lot of things that we can do even with our models before we deploy them. Maybe we don't have to just deploy and then wait for a journalist to come along and say, well, you're actually biasing against this group of people, or you're not providing recourse to a bunch of people. Cool.
So I'm only somewhat on the technical side. I was wondering, you mentioned how his application for journalists for actionable recourse, if you had any specific examples of how it applied to journalists.
Yeah, I mean, welcome. It's nice. I mean, I'm coming from that background too, so I'm broadly interested in how to help journalists. I think that the closest example is just giving another way to reverse engineer black box models that we see in society. So I mean, the example with Wired sort of querying Google's photo tagging gives a sort of picture about how journalists are able to interrogate models. And once you can interrogate a model and get sort of the input and outputs of that model, then you can start to make statements about what is the model actually doing. But it's certainly a challenging problem because often you face challenges in getting a large enough training set from just querying a black box model. And I think you'd have to find the right domain, but I'd be curious to chat afterwards. Yeah. In short, we need more tools to understand what's happening in society, and even transparent models might not provide recourse simply in the way variables are encoded, the deployment population, modeling choices, and then large, costly changes that we're asking users to make. I have a demo, but I don't know that I have time for that. There's a lot of information that we have online. We have the entire code open source, so check out our repository on GitHub, which is just Recourse. We have our paper online. We have some press coverage about this if you want to explore more. And check out my various collaborators' homepages. Thank you so much for your time.